P equals A times A transpose A inverse times A transpose. This formula is the workhorse of projections, least squares, and regression. But notice this middle piece, A transpose A inverse. It demands a matrix inversion, which is expensive and error-prone. Now watch what happens. When the columns of A are orthonormal, we call that matrix Q. Q transpose times Q equals the identity matrix, so its inverse is just the identity. The formula collapses beautifully. P equals Q times Q transpose, no inverse anywhere. Let's see where this comes from. Here's the projection problem. We have a vector B and a subspace, the column space of a matrix A. We want to find the closest point to B in that subspace. That closest point is the projection P. A projection matrix sends any vector to its closest point in a subspace. The error vector E equals B minus P, and it drops perpendicular to the subspace. Now the formula for the projection matrix, P equals A times the quantity A transpose A inverse times A transpose. Multiply any vector B by this matrix P, and out comes its projection onto the column space of A. The cost centers on one operation, inverting A transpose A. For large matrices, this matrix inversion is the computational bottleneck. A matrix Q has orthonormal columns when two conditions are satisfied. First, each column has unit lengths, meaning the norm of Qi equals 1. Second, distinct columns are perpendicular, meaning Qi transpose times Qj equals 0 whenever I is not equal to j. Both of these conditions pack neatly into one single equation, Q transpose, Q equals the identity matrix. Let's see a concrete example. Define Q1 as the vector 1 over root 2, 1 over root 2, and define Q2 as the vector negative 1 over root 2, 1 over root 2. Now form the matrix Q with these as columns, and compute Q transpose Q entry by entry. The 1, 1 entry is Q1 dot Q1, that's 1/2 plus 1/2, which equals 1. The 1, 2 entry is Q1 dot Q2, that's negative 1/2 plus 1/2, which equals 0. By symmetry, the 2, 1 entry, Q2 dot Q1, also equals 0, and the 2, 2 entry is Q2 dot Q2, 1/2 plus 1/2, which equals 1. The result is the 2 by 2 identity matrix. This single fact, Q transpose Q equals I, is what drives every simplification ahead. Now let's substitute Q into the projection formula. P equals Q times the inverse of Q transpose Q times Q transpose. We showed in the previous frame that Q transpose Q equals the identity matrix I, so we substitute that in. P equals Q times I inverse times Q transpose. But the inverse of the identity is just the identity itself. So P equals Q times I times Q transpose, and Q times I is simply Q. So our final result is P equals QQ transpose. The inverse has completely vanished. This is a beautiful simplification. Let's see a concrete example to make this real. Let Q be a 3 by 2 matrix with columns Q1 equals 1 over the square root of 2, 1 over the square root of 2, 0, and Q2 equals 0, 0, 1. Now let's compute QQ transpose. For the first row, 1 over root 2 times 1 over root 2 is 1/2. 1 over root 2 times 1 over root 2 is 1/2. And 1 over root 2 times 0 plus 0 times 1 is 0. For the second row, similarly, we get 1/2, 1/2, 0. For the third row, 0, 0, 1. So the 3 by 3 projection matrix is row 1 is 1/2, 1/2, 0. Row 2 is 1/2, 1/2, 0. Row 3 is 0, 0, 1. Notice this is not the identity matrix. It projects onto the two-dimensional column space of Q inside R3. And the key point is no matrix inversion was required. The normal equations for least squares, the equations that come from minimizing the squared error, B minus AX, are A transpose A X hat equals A transpose B. Now let's substitute Q in place of A. We get Q transpose Q X hat equals Q transpose B. But we know that Q transpose Q is the identity matrix I, so this simplifies to I times X hat equals Q transpose B. That means X hat simply equals Q transpose B. And if we expand this component-wise, each coefficient X hat I equals Q I transpose B. In other words, each coefficient is just a single dot product. Let's use our 3×2 Q from before with B equals 1, 2, 3. X hat 1 equals Q1 dot B. That's 1 over root 2 times 1 plus 1 over root 2 times 2 plus 0 times 3, which gives 3 over root 2. X hat 2 equals Q2 dot B. That's 0 times 1 plus 0 times 2 plus 1 times 3, which gives simply 3. Notice how beautifully simple this is. Each coefficient requires just one dot product, no matrix inversion at all. We derived that P equals QQ transpose. Now let's verify that it behaves like a proper projection matrix. There are two properties we need to check: symmetry and idempotence. First, symmetry. This means P must equal its own transpose. Let's take the transpose of QQ transpose. Remember, the transpose of a product reverses the order of the factors. So we get Q transpose times Q transpose. Now Q transpose just gives us back Q, and Q transpose is Q transpose. So we end up with Q times Q transpose, which is exactly what we started with. P transpose equals P, symmetric, done in one line. Now for idempotence, this means projecting twice should be the same as projecting once, which requires that P squared equals P. Let's compute QQ transpose times QQ transpose. The key is to focus on the middle two factors, Q transpose times Q, but we know from orthonormality that Q transpose Q equals the identity matrix I, so the whole product becomes Q times I times Q transpose, which simplifies to just QQ transpose. P squared equals P, confirmed. Notice the key move here. Q transpose Q appeared sandwiched in the center of the expression and collapsed to the identity. That single collapse is exactly why orthonormality makes projections so clean. Now let's look at an important special case. When Q is square, meaning it has n orthonormal columns in Rn, its column space is all of Rn. Projecting onto the full space changes nothing, so the projection must be the identity matrix. The formula confirms this. Let's take the 45-degree rotation matrix as our example. Q equals, row 1 is root 2 over 2, negative root 2 over 2. Row 2 is root 2 over 2, root 2 over 2. Now let's compute Q times Q transpose and check each entry. For entry 1, 1, we compute root 2 over 2 squared plus negative root 2 over 2 squared. That gives 1/2 plus 1/2, which equals 1. For entry 1, 2, we compute root 2 over 2 times root 2 over 2 plus negative root 2 over 2 times root 2 over 2. That gives 1/2 minus 1/2, which equals 0. Entry 2, 1 is 0 by the same reasoning. And for entry 2, 2, we get root 2 over 2 squared plus root 2 over 2 squared, which is 1/2 plus 1/2 equaling 1. So the result is the 2×2 identity matrix. This confirms our claim. When Q is square, Q times Q transpose equals the identity, and therefore Q transpose equals Q inverse. This is precisely the defining property of an orthogonal matrix. Contrast this with the 3×2 case from earlier, where QQ transpose was not the identity because Q was not square. Now let's compare these two approaches side by side. On the left, we have a general basis A. The projection matrix is P equals A times A transpose A, inverse times A transpose. To find the coefficients, you must solve the normal equation. A transpose A times X hat equals A transpose B. The key operation here is matrix inversion, specifically inverting A transpose A, and the computational cost is on the order of n-cubed operations. On the right, we have an orthonormal basis Q. The projection simplifies dramatically. P equals QQ transpose. The coefficients are simply dot products. x hat sub I equals q sub I transpose times b. The key operation is just dot products, and the cost drops to order m times n operations. That's a huge computational savings. But here's the practical bridge connecting these two worlds. Any general basis can be converted into an orthonormal basis using the Gram-Schmidt process, or equivalently QR factorization. So in practice, you can always get the benefits of the orthonormal case. Orthonormal bases are the preferred currency of applied mathematics. Let's see why this one elegant formula connects to so many important applications. The key takeaway is this: x hat I equals q I transpose times b, one dot product per coefficient. This works because of a universal pattern. Whenever you have an orthonormal basis, computing coefficients reduces to simple dot products. Let's see where this pattern appears. First, in Fourier series, Fourier coefficients are computed as inner products with orthonormal sines and cosines. The trigonometric functions form an orthonormal basis, so extracting each frequency component is just a dot product. Second, in principal component analysis, or PCA, projections onto principal components work the same way. The eigenvectors of the covariance matrix form an orthonormal basis, and projecting data onto each component is again a dot product. Third, in QR decomposition. QR decomposition converts any matrix into orthonormal form, which provides numerical stability for solving least squares problems. This is exactly the Gram-Schmidt process we discussed earlier put into practice. Fourth, in signal processing, the discrete Fourier transform and fast Fourier transform exploit orthonormality to efficiently decompose signals. The entire FFT algorithm relies on the orthonormality of complex exponentials. The pattern is universal. Invest upfront in building an orthonormal basis, and every downstream computation, projections, least squares, coefficient extraction becomes simple dot products.